A railgun is an electromagnetic projectile launcher based on similar principles to the homopolar motor. A railgun comprises a pair of parallel conducting rails, along which a sliding armature is accelerated by the electromagnetic effects of a current that flows down one rail, into the armature and then back along the other rail. Railguns are being researched as a weapon that would use neither explosives nor propellant, but rather rely on electromagnetic forces to achieve a very high kinetic energy of a projectile. While explosive-powered military guns cannot readily achieve a muzzle velocity of more than about 2 km per second, railguns can readily exceed 3 km per second, and thus far exceed conventionally delivered munitions in range and destructive force, with the absence of explosives to store and handle as an additional advantage. In addition to military applications, NASA has proposed to use a railgun from a high-altitude aircraft to fire a small payload into orbit. However, the extreme G-forces involved would necessarily restrict the usage to only the sturdiest of payloads. Basics. In its simplest form, the railgun differs from a traditional electric motor in that no use is made of additional field windings. This basic configuration is formed by a single loop of current and thus requires high currents to produce sufficient accelerations. A relatively common variant of this configuration is the augmented railgun, in which the driving current is channeled through additional pairs of parallel conductors, arranged to increase the magnetic field experienced by the moving armature. These arrangements reduce the current required for a given acceleration. In electric motor terminology, augmented railguns are usually series wound configurations. The armature may be an integral part of the projectile, but it may also be configured to accelerate a separate, electrically isolated or non-conducting projectile. Solid, metallic sliding conductors are often the preferred form of railgun armature, but plasma, or hybrid, armatures can also be used. A plasma armature is formed by an arc of ionized gas that is used to push a solid, non-conducting payload in a similar manner to the propellant gas pressure in a conventional gun. A hybrid armature uses a pair of plasma contacts to interface a metallic armature to the gun rails. Solid armatures may also transition into hybrid armatures, typically after a particular velocity threshold is exceeded. A railgun requires a pulsed direct current power supply. For potential military applications, railguns are usually of interest because they can achieve much greater muzzle velocities than guns powered by conventional chemical propellants. Increased muzzle velocities can convey the benefits of increased firing ranges, while, in terms of target effects, increased terminal velocities can allow the use of kinetic energy rounds as replacements for explosive shells. Therefore, typical military railgun designs aim for muzzle velocities in the range of 2,000 to 3,500 meters per second with muzzle energies of 5 to 50 megajoules. For comparison, 50 megajoules is equivalent to the kinetic energy of a school bus weighing 5 metric tons, traveling at 509 kilometers per hour. For single-loop rail guns, these mission requirements require launch currents of a few million amperes. So a typical railgun power supply might be designed to deliver a launch current of 5 megaamperes for a few milliseconds, as the magnetic field strengths required for such launches will typically be approximately 10 Tesla. Most contemporary railgun designs are effectively air-cored, i.e., they do not use ferromagnetic materials such as iron to enhance the magnetic flux. It may be noted that railgun velocities generally fall within the range of those achievable by two-stage light gas guns. However, the latter are generally only considered to be suitable for laboratory use, while railguns are judged to offer some potential prospects for development as military weapons. Another light gas gun, the Combustion Light Gas Gun in a 155 mm prototype form, was projected to achieve 2,500 meters per second with a 70 caliber barrel. In some hypervelocity research projects, projectiles are pre-injected into rail guns to avoid the need for a standing start, and both two-stage light gas guns and conventional powder guns have been used for this role. In principle, if railgun power supply technology can be developed to provide compact, reliable and lightweight units, then the total system volume and mass needed to accommodate such a power supply and its primary fuel can become less than the required total volume and mass for a mission-equivalent quantity of conventional propellants and explosive ammunition. Such a development would then convey a further military advantage in that the elimination of explosives from any military weapons platform will decrease its vulnerability to enemy fire. History. In 1918, French inventor Louis-Octave Fauchon-Villepilly invented an electric cannon, which is an early form of rail gun. He filed for a U.S. patent on 1 April 1919, which was issued in July 1922 as Patent No. 1,421,435, electric apparatus for propelling projectiles. In his device, two parallel bus bars are connected by the wings of a projectile, and the whole apparatus surrounded by a magnetic field. By passing current through bus bars and projectile, a force is induced which propels the projectile along the bus bars and into flight. In 1944, during World War II, Joachim Hansler of Germany's Ordnance Office proposed the first theoretically viable rail gun. By late 1944, the theory behind his electric anti-aircraft gun had been worked out sufficiently to allow the Luftwaffe's Flak Command to issue a specification, which demanded a muzzle velocity of 2,000 meters per second and a projectile containing 0.5 kilograms of explosive. The guns were to be mounted in batteries of 6 firing 12 rounds per minute, and it was to fit existing 12.8 cm Flak 40 mounts. It was never built. When details were discovered after the war, it aroused much interest and a more detailed study was done, culminating with a 1947 report which concluded that it was theoretically feasible, but that each gun would need enough power to illuminate half of Chicago. During 1950, Sir Mark Oliphant, an Australian physicist and first director of the Research School of Physical Sciences at the New Australian National University, initiated the design and construction of the world's largest homopolar generator. This machine was operational from 1962 and was later used to power a large-scale railgun that was used as a scientific experiment. Late into the first decade of the 2000s, the U.S. Navy tested a railgun that accelerates a 3.2 kilograms projectile to hypersonic velocities of approximately 2.4 kilometers per second, about Mach 7. They gave the project the Latin motto, Velocitas Eradico, Latin for I, who am, speed, eradicate. Design. Theory. A railgun consists of two parallel metal rails connected to an electrical power supply. When a conductive projectile is inserted between the rails, it completes the circuit. Electrons flow from the negative terminal of the power supply up the negative rail, across the projectile, and down the positive rail, back to the power supply. This current makes the railgun behave as an electromagnet, creating a magnetic field inside the loop formed by the length of the rails up to the position of the armature. In accordance with the right-hand rule, the magnetic field circulates around each conductor, since the current is in the opposite direction along each rail. The net magnetic field between the rails is directed at right angles to the plane formed by the central axis of the rails and the armature. In combination with the current in the armature, this produces a Lorentz force which accelerates the projectile along the rails. away from the power supply. There are also Lorentz forces acting on the rails and attempting to push them apart, but since the rails are mounted firmly, they cannot move. By definition, if a current of 1 ampere flows in a pair of infinitely long parallel conductors that are separated by a distance of 1 meter, then the magnitude of the force on each meter of those conductors will be exactly 0.2 micronewtons. Furthermore, in general, the force will be proportional to the square of the magnitude of the current and inversely proportional to the distance between the conductors. It also follows that, for railguns with projectile masses of a few kilogram and barrel lengths of a few m, very large currents will be required to accelerate projectiles to velocities of the order of 1,000 meters per second. A very large power supply, providing on the order of 1 million amperes of current, will create a tremendous force on the projectile, accelerating it to a speed of many kilometers per second. 20 kilometers per second has been achieved with small projectiles explosively injected into the railgun. Although these speeds are possible, the heat generated from the propulsion of the object is enough to erode the rails rapidly. Under high-use conditions, current railguns would require frequent replacement of the rails, or to use a heat-resistant material that would be conductive enough to produce the same effect. At this time it is generally acknowledged that it will take major breakthroughs in material science and related disciplines to produce high-powered rail guns capable of firing more than a few shots from a single set of rails. The barrel must withstand these conditions for up to several rounds per minute for thousands of shots without failure or significant degradation. These parameters are well beyond the state-of-the-art in material science. Mathematical formula: the magnitude of the force vector can be determined from a form of the Biot-Savart law and a result of the Lorentz force. It can be derived mathematically in terms of the permeability constant and the current in amps through the system from the end of the wire is given by. Note this is if the wire runs from the location of the armature, e.g., from x equals 0 back to and is measured relative to the axis of the wire. So, if the armature connects the ends of two such semi-infinite wires separated by a distance, a fairly good approximation assuming the length of the wires is much larger than the total field from both wires at any point on the armature, or any point in the plane between the two wires is, whereas the perpendicular distance from the point on the armature to the axis of one of the wires. Note that between the rails is assuming the rails are lying in the xy plane and run from x equals 0 back to as suggested above. To obtain an approximate expression for the force on the railgun armature, we start by again assuming that the railgun rails can be modeled as a pair of semi-infinite conductors. This allows us to use the above expression for the magnetic field on the armature in the Lorentz force law. Inserting the expression for the magnetic field into the Lorentz force law and setting the bounds of integration to in. Assuming the armature is a bar between and perpendicular to the rail's making point in the, we find the force on the armature is the formula is based on the assumption that the distance is measured and the beginning of the rails is greater than the separation of the rails. Some other simplifying assumptions have also been made to describe the force more accurately. The geometry of the rails and the projectile must be considered. With most practical railgun geometries, it is not easy to produce an electromagnetic expression for the railgun force that is both simple and reasonably accurate. Instead, most practical railgun analyses actually used a lump circuit model to describe the relationship between the driving current and the railgun force. In these models the voltage across the railgun breech is given by, then the barrel resistance and inductance are assumed to vary linearly with the projectile position, so that from which if the driving current is held constant, there is a power flow equal to which represents the electromagnetic work done. In this simple model, exactly half of this is assumed to be needed to establish the magnetic field along the barrel, i.e., as the length of the current loop increases, The other half represents the power flow into the kinetic energy of the projectile. Since power can be expressed as force times speed, this gives the standard result that the force on the railgun armature is given by. This simple equation shows that high accelerations will require very high currents. For an ideal square-bore railgun, the value of would be about 0.6 microhenries per meter, but most practical railgun barrels exhibit lower values than this. Since the lumped circuit model describes the railgun force in terms of fairly normal circuit equations, it becomes possible to specify a simple time domain model of a railgun. Ignoring friction and air drag, the projectile acceleration is given by, where m is the projectile mass. The motion along the barrel is given by, and the above voltage and current terms can be placed into appropriate circuit equations to determine the time variation of current and voltage. It can also be noted that the textbook formula for the high-frequency inductance per unit length of a pair of parallel round wires of radius r and axial separation d is, so the lumped parameter model also predicts the force for this cases. With practical railgun geometries, much more accurate 2- or 3-dimensional models of the rail and armature current distributions can be computed, e.g., by using finite element methods to solve formulations based on either the scalar magnetic potential or the magnetic vector potential. Design considerations: the power supply must be able to deliver large currents, sustained and controlled over a useful amount of time. The most important gauge of power supply effectiveness is the energy it can deliver. As of December 2010, the greatest known energy used to propel a projectile from a railgun was 33 megajoules. The most common forms of power supplies used in railguns are capacitors and compulsators, which are slowly charged from other continuous energy sources. The rails need to withstand enormous repulsive forces during shooting, and these forces will tend to push them apart and away from the projectile. As rail-projectile clearances increase, arcing develops, which causes rapid vaporization and extensive damage to the rail surfaces and the insulator surfaces. This limited some early research railguns to one shot per service interval. The inductance and resistance of the rails and power supply limit the efficiency of a railgun design. Currently, different rail shapes and railgun configurations are being tested, most notably by the United States Navy. The Institute for Advanced Technology at the University of Texas at Austin, and BAE Systems. Materials used: the rails and projectiles must be built from strong conductive materials. The rails need to survive the violence of an accelerating projectile and heating due to the large currents and friction involved. Some erroneous work has suggested that the recoil force in railguns can be redirected or eliminated. Careful theoretical and experimental analysis reveals that the recoil force acts on the breech closure just as in a chemical firearm. The rails also repel themselves via a sideways force caused by the rails being pushed by the magnetic field, just as the projectile is. The rails need to survive this without bending and must be very securely mounted. Currently published material suggests that major advances in material science must be made before rails can be developed that allow railguns to fire more than a few full power shots before replacement of the rails is required. Heat dissipation in current designs: massive amounts of heat are created by the electricity flowing through the rails, as well as by the friction of the projectile leaving the device. The heat created by this friction itself can cause thermal expansion of the rails and projectile, further increasing the frictional heat. This causes three main problems: melting of equipment, decreased safety of personnel, and detection by enemy forces due to increased infrared signature. As briefly discussed above, the stresses involved in firing this sort of device require an extremely heat-resistant material. Otherwise the rails, barrel, and all equipment attached would melt or be irreparably damaged. In practice, the rails are, with most designs of railgun, subject to erosion due to each launch. In addition, Projectiles can be subject to some degree of ablation, and this can limit railgun life, in some cases severely.